Part A. All right. Which of the following statements best describes the characteristics of the restoring force in the spring mass system described in the introduction? The restoring force is what brings the spring back to its initial position.
Mm-hmm.
It seems like it's, well, I don't even know if I want to say, but it's not constant. I could probably say that for sure. Let me get back to where I can look up a reference for this.
It overwhelmingly says restoring force is directly proportional to the displacement of the block.
It looks like it's B there. All right. So part B, it says a coordinate system with the origin at the equilibrium position is shown, so that the x-coordinate represents the displacement from the equilibrium position. The positive direction is to the right. What is the initial acceleration of the block released at a distance A? So we're trying to find that. So they say, okay, they say F equals minus kx, but x in this case is a distance A. So instead of it being minus kx, it'll be minus ka. And then from your formulas, the acceleration is F over m. So we have F over m is going to I'm sorry, we can substitute in for F minus Ka over m for that. So that's part B.
What does AO stand for?
Initial acceleration.
Initial acceleration? Okay. That's correct. On to C.
All right, so when the block is at its equilibrium position, the acceleration is 0. So if the block is moving left or right, it has an acceleration, but right here, the acceleration is equal to 0 for part C.
That's correct. On to D. Oh, it did not show it for you for D?
It does not show me part D, although I might be able to find it. Nope, it's not open.
In case that doesn't work, I'm gonna just screenshot it and I'm gonna send it in your reply, attaching it right now. And bada bada boom. That should be it. There, set.
Okay, I'll check that out.
Select the correct expression that gives the block's acceleration at displacement x from the equilibrium position.
So we just did that. It's minus km over times x, letter D. I mean, we just I mean, that's here. So the only other possible one would be C because of the sign. You can also just search for it just to double check if you want to take the time for us to do that. That's okay. Select the correct. All right, so part D here is yeah, it's this minus Ka over m, but A is really x, so minus Kx over m for that. So you want to select that fourth option, please.
That's correct. All right.
Okay, so the next one is the magnitude of the block's acceleration reaches its maximum value when. So we know that at here it's 0.
At the equilibrium.
Yeah, so that's definitely not there. And then it actually reaches its a max either here or here, like wherever it's at its extreme endpoints. So that's letter B, it looks like.
That's correct. On F, the speed of the block is 0 when.
So this is where it's you got to really understand the difference between speed and velocity. So the speed, the velocity is 0 when it is at the left or the rightmost endpoint, because it's momentarily not moving.
Is it equilibrium position? Leftmost?
No, it's leftmost or rightmost endpoint. So even though it's accelerating, it's not moving at its endpoints when it gets to the ends here. Let me see if I can pull up the pull that one up so I can tell you which letter to select, because I guess it's not. It's B at either its rightmost or leftmost endpoint.
That's correct.
It reaches its maximum value. So if it's 0 at the endpoints, well, when it's back at the starting point, right in the middle, that's where it's going the fastest.
Okay. On to part H. Do you not have that part on your side? Because I can send it to you.
I see part of it. Yeah, okay. So it says, it just asks for the equation for the velocity and the acceleration. These are well-known things. They are like, I don't know, they're like things that they're just like sort of given. So V is minus B sine omega t. So that's either A, C, or D. And then the other one is minus C cosine omega t. So that gets us down to letter D, it looks like, for that one.
All right. Let's get on to number 7.
This is another conceptual problem. It looks like they don't give you more than part A. So part A is asking what effect, let me snip it in, it's saying what effect does the dropping the sandbag have on the equilibrium position? So currently the mass on the cart is the person M plus big M. Is that okay? I mean, is that clear? Like
Yes.
And then when you throw it off, well, what's going to happen? So there's really only two reasons why, which is either it increases or decreases. And I'm not sure I can provide a great explanation, but it does decrease the amplitude. The energy of the system is 1/2 Ka squared. And probably because energy is associated with mass, like the more mass, this E is maybe associated with like 1/2 mv squared. Well, if it's equal to 1/2 Ka squared, if m goes down, then A also has to go down. So that's why it decreases
the amplitude. All right.
So part B, I don't have a picture for.
Oh,
So I'm
okay.
not sure.
I'll send it right on over.
But it says something about instead of dropping the sandbag as you pass through equilibrium, you just try to drop the sandbag when the card is its maximum distance. So because it's already at the maximum distance, the like that's as fast as it's going to go. So dropping the bag won't have any effect. Like it won't change the speed. Is there an option that says don't change the speed?
Yes.
Okay.
Next is what effect does dropping the sandbag at the cart's maximum distance from equilibrium have on the amplitude of your oscillation?
So again, there's no change in the amplitude because you're doing it at the maximum displacement.
That's correct. What effect does dropping the sandbag at the cart's maximum distance on the cart? Hmm. Does it have
So
does it have an effect on the cart?
well, yeah, like we're talking about part D now.
Yeah.
So part D maybe says something about so it's this equation here, but this time the A is staying the same. So if M, it's like looking at this equation. It's like, well, how does this equation, if it has to stay the same, if M goes down, then V has to go up because this is the same on the right here.
Oh, okay.
And if you had a lab, I guess this would be one of those things they put in the lab, and you would see that maybe. I don't know if you're doing any labs, but
All right, on to energy of harmonic oscillators.
okay. So not gravity on another planet.
We can do that. Which one is?
That's the order they came in. So which?
Oh, we can do that. Let's get to it.
Yeah. So what I'm seeing is the only one. The next one is gravity on another planet. Then problem 11.16, 11.27, and that's it.
I can send you some more problems.
Okay. Do you want me to wait for those or look at this one first?
Let's just look at this one first. Let's keep it moving.
Okay, so I'm snipping it in here. After landing on an unfamiliar planet, a space explorer constructs a simple pendulum of length. Okay, and then four full swings. Okay, so there's some formula for length of a pendulum and period and a bunch of things like that. So let me see if I can find it. All right, so the period here is, and this is a formula, is 2 pi square root L over G. You seen that before?
Sure.
So I don't really like, so the period is the time that's given. So that's the number, the total time divided by the number of full swings. So T in this case is 126 divided by 104 full swings. And then L is given as in centimeters, so we need to convert that to meters. So it's 49 over 100. Gets that right. And then we're just solving for G, I believe. We're just solving for the G in this case. So we can do that, and then we just stuff the numbers in. We have T divided by 2 pi, then we square it, and that gets you to L over G. So since we want G, we just swap positions here. It's L over T over 2 pi squared. Sometimes what they do is they distribute this and they multiply, so it ends up being 4 pi squared L over T. And so that's 4 pi squared. The L is the 49 over 100, and the T is 126 over 104.
Just calculate that out.
Yep. So let me help here. 4 pi squared. And I get how many decimal places does it want us to round to?
It says to the nearest. Wait.
So I get like 15.97, so maybe 16.0
See if
meters per second.
Nope, it still wants me to do it all the way. 15.966. It says it's all wrong. All of the ones that I put in 15.97. That's odd. And we don't need to get stuck on this. We can go to another problem.
All right. Well, I mean, so I looked at just one more reference, and it's there. Yeah. 2 pi. It's 2 pi, right? 2 pi. 4 pi squared. 4 pi squared L. Yeah. Okay. Well, that's what it is. Okay. So we're up to problem 1116. That's what I see next on the screen here. I'm gonna pull up the chapter solutions so I can go through these faster. Give me a moment just to find those. Seems like I'm there. Okay, we're on chapter 11, problem 16. Takes a force 83.5 newtons to compress the spring of a toy pop gun, 0.16 meters to load, at 0.55 kilogram ball. What is the velocity that the ball leaves? Okay, so they actually give you this. They give you a formula. They say V max, or V, is amplitude square root K over M.
Mm-hmm.
But you don't have some of these values. I mean, you have the mass. You have A, that's 0.16. You can find K. K is F equals Kx, is the relationship between force and the spring constant. So in this case, K is equal to F over X. The force is 83.5 newtons and 0.160 meters.
Mm-hmm.
Right. And then so we have everything. So V is equal to the point, the A and X are equal in this problem because it's already stretched. So that's 0.160 square root of so that K value, which they calculate as an intermediate step, but 83.5 or 0.16 over the mass, which is 0.155. Okay, so let me help calculate this. 0.16 times square root, and then 83.5 divided by 0.16 divided by 0.155. All right, so I get 9.28
9.28. All right.
meters per second for that.
42. All right. That's correct. On to 1127.
All right, let me get back to where I've got that question. Okay, there it is, 1127. Pendulum has a period on Earth, and then they want to know what's going on probably on Mars for some reason.
Mm-hmm.
All right, so we got 1127. All right, so we know that the period, this is that same equation we're having issues with, it's 2 pi square root L over G. And we know that on Mars, we get the same thing, like it's the same equation. What they do here is they do one for Earth and then for Mars. So T Mars equals 2 pi square root L over G Mars. And then they take the ratio. They take the ratio of Tm over Te, and a lot of things cancel. So like it's 2 pi square root L over G M over 2 pi square root L over GE.
What's L stand for in this case?
Length of the pendulum.
Length of pendulum.
So these cancel. And then you get the L's ends up canceling, and there's a flip, so you get the square root of GE over GM. Okay, so the relationship here is that TM equals TE square root GE over GM.
Okay.
And now we have some values. We are told in the problem that the ratio of the two planets is 0.37. So that means that GE over GM equals, well, it's actually the other way around. So they actually do it this way. They say GM over GE equals 0.37. But since we want the flip of that, we take the flip of the number on the right.
Oh.
Okay. So then that's the square root of 1 over 0.37. And then they tell you the period is 1.52 seconds on Earth. So this is our, yeah.
Huh.
So it ends up being 2.5 seconds.
That's correct. All right, what's the next problem that I sent you for?
Yeah, I'll check it out here. I see that you've got, you sent some screenshots. Okay, sorry to look at that one.
I sent you the harmonic oscillator one.
I'm seeing everything that I don't see anything that we haven't done yet, but let me look one more time. 16, 27, yeah. So just send me a new batch here. We'll get through as many as we can.
I think we'll get through the ones I want to get through today. Here we go. Apply. Send these last two.
Okay, I see that some new pictures have come in. All right, so the first one is about a pendulum lab tutorial. So did you drag the pendulum to, I mean, have you followed these steps, like set the friction to none, go to 30 degrees?
Not yet.
Okay.
Let me pull this up. All right, so we're in the intro. Set the pendulum to 30 degrees. Minus 30 degrees. Be sure to set friction to none. Friction set none. Drag the pendulum to 30 degrees. Release it. So once it gets to negative 30 degrees, what forms of energy does it have?
Yeah, so now it started at 30, and then it goes the other direction. So it definitely has potential energy because it's above where it started. Although that's interesting. Maybe because what's really unclear to me is whether it's referring to compared to its initial position or either of these positions. At any other point, does it move beyond the? No, it would just go back and forth.
I think it's just potential energy.
If it's not moving, there's no kinetic energy. I will look and see if this is solved somewhere, because that's really, I mean, these are not. It does look like these are going to be here. Maybe. I'm not seeing anything here that's very helpful. Did you try kinetic and potential, or just potential?
I put potential in there and it said it was correct.
Okay.
Drag
I don't have.
Drag a pendulum to an angle. Huh. So it has the most energy when it's at 0 degrees.
Okay, and that's probably because it's good. It's moving
To the right because of.
Yeah.
Drag the pendulum to an angle with the respective 30 degrees and then release it and show the acceleration vector. And select to show the acceleration vector.
So what do you want me to do here? Because I'm sort of unable to help much without either more pictures or.
I get some more photos your way.
I know it's a little slow to go back and forth, but
That's okay. I got it. Here's that. Send. There we go. Is the acceleration ever 0 during a pendulum?
yeah, it's 0 at the bottom of the pendulum, wherever it hits the bottom. So when the angle is 0. Yeah, it's very similar to the spring mass that's going back and forth.
With the pendulum for part C, the answer was the acceleration is never equal to 0 as it swings back and forth.
Okay.
This next one, the pendulum swinging back and forth, how does the tension of the rope compare to the force of gravity when the angle is 0 degrees?
So the tension is greatest at the bottom because the all of the tension is being reacted on by the force, whereas when it swings to the left or right, there's a tension vector going out to the right or the left that's not affected by gravity.
So is the tension greater than the force of gravity or less, or is it just?
It should be this. I mean, it should be the same because otherwise it would fly off, or maybe less. I mean, if the tension was more, it would pull up.
The answer is that it's greater.
Okay.
Drag the pendulum with respect vertical to 90 degrees and release it with the pendulum swinging back and forth. The tension is never zero. What? No. I'm going to send you a photo of this one. This one's particularly long.
Okay. So this is all based on going through the tools above and getting the number based on that. Like, I don't have any way to help you on this other than to do it, which I don't have access to. I'm not seeing this online in a way where I can just, if somebody's already said, oh, here's the answers. I'll look though.
What does a period of oscillation mean?
The number of oscillations per second. Like, so like in a earlier problem we did, like, oh, it does 90 oscillations in 100 seconds.
Oh. Oh, what's the period to complete 10 swings? Here we go.
I mean, I mean, I've got kind of a solution here, but it's just the answer. It's 1 period in 2 seconds. So 2 seconds is the period.
And that's correct. On to G. How does the period of oscillation depend on the initial angle of the pendulum when released?
If there's no friction, it doesn't seem like it should matter. Like, it should be the same.
All right, on to part H. A heavier pendulum has a shorter period. A heavier pendulum has a longer period. The period is independent of the pendulum's mass. I think it's going to be shorter. Nope. It's heavier. Independent.
So mass must cancel out.
Now keep the mass fixed to any angle you choose and measure the period of several different pendulum lengths. How does the period of the pendulum depend on the length? The period is independent. Nope, it's a longer pendulum, has a longer period. All right. Now we're done with the period lab. Let's go on to, what was it? Did we finish harmonic motion? 3, 4, 5, 6, 7, yep. Let's go with that. Did I send you the harmonic oscillators? That's the last one I want to go through.
Okay. I don't have any more pictures that to pull up.
Here we go. I just sent the screenshot.
Okay. There it is. Okay, yeah, I guess you did send this. Okay. Which moment corresponds to the maximum potential energy of the system? So moment. So the potential energy in a spring is 1/2 kx squared. So it gets bigger as you get further away from the original position. So it looks like it's A, but you can definitely I think this one might be more searchable. So yeah, I'm getting another confirmation that it's at point A.
That it's A. Okay.
Yeah, that's where it's furthest from the original position.
That's correct. Which moment corresponds to the minimum kinetic energy of the system?
So that's where the velocity is 0. We know that the velocity is 0 when it gets all the way to the right or the left, like its maximum position. So that again is at A because that's all the way to the right before it starts coming back.
Okay. That's correct. Consider the block in the process of oscillating. If the kinetic energy of the block is increasing, the block must be.
What is it asking for? I don't have the picture. I don't have that part. Is that for the energy?
If the kinetic energy of the block is increasing, the block must be either increasing, moving to the left, right, or something else.
Okay, so they show the calculation of the kinetic energy going from 1/2 to 3/8, which is getting smaller. There's no confirmation of that though. It's not words. It's not like moving toward equilibrium.
It is moving toward equilibrium.
Okay.
Or away from it.
So it is moving towards equilibrium, I believe.
That's correct. Which moment corresponds to the maximum kinetic energy of the system? Is that D?
It's C because it's right back where we're at the origin where it started, and where it started it has the velocity is the greatest.
That's correct. Which moment corresponds to the minimum potential energy of the system? Is that D?
So it's at where it started at that origin position.
Is that C?
Yes, that's C.
That's correct. At which moment is K equal to U?
Okay, so that's where the energies are the same. So like one increases, the other. Oh no, they're the same when the spring is most stretched and the velocity is the greatest. So somewhere in between.
It's D for this one.
Okay.
Find the kinetic energy K of the block at the moment labeled B.
Okay, so they do this long calculation, and that's the one that's 3/8 kVA squared.
KV. 8 squared.
A, big capital A squared.
Are K and V undercase or lowercase?
I'm written much here, but it looks like this according to the thing I'm looking at. KV big A squared.
The correct answer does not depend on KVA.
Oh, there is no V. I'm sorry. It's 3/8 KA squared.
And that's correct. Let's get into that. All right. Could we try looking over the gravity on another planet one again?
Sure. I have no idea why it's not right, so I'll look at it again. 1 in 4 full swings. Maybe that is the wrong one. Maybe it was something else. Oh, I see. So I did not square this number down here. That's why it was wrong. Okay, that will fix that. So let me get back to that calculation. There it is. All right, so I get 13.18, and that's meters per second.
All right.
All right. Thanks for scheduling, Jack. I'll send the notes and the screen recording out shortly.
13.18, right?
Yeah.
13.18. That's correct. Thank you. I appreciate you.
All right. I'll see you next time. Yep. Have a great day.
You too. Thank you.